Hi everyone, I'm John Turilla, one of the authors of Topology, a Categorical Approach. In this video, I'm going to talk about filters and ultrafilters in topology. Let's begin with the definition. A filter on a set X is a collection of subsets of X satisfying some properties. Namely, it's downward directed. That means that if A and B are in the collection, their intersection is in the collection. We also require that the collection be non-empty, there be some sets in the collection, and that it be upward closed, meaning if A is in the collection and A is contained in another set B, then B is in the collection. It's often convenient to think of filters in another equivalent way, namely as functions from the power set of X into 0, 1 that are compatible with the binary operation of intersection and respect the identity for intersection. And then you move between these two perspectives. If you have a function from the power set into 0, 1, you get a collection of subsets as the preimage of 1. Now, let's look at some examples. So, you can take the full collection, the power set of X. That's called the improper filter. That's the same as saying the empty set is in F because F is upward closed. So once you have the empty set, you have everything. There's something called the principal filter that depends on a point, little x in F. And that's just the set of all sets A that contain the point X. Now, I think of principal filters as points because you can think of a point as a function from the one element set into X. And then you can pull back subsets of X to get subsets of the point, and that map from the power set of X to 0, 1 is exactly a principal filter. Now there is a trivial filter. By definition, filters can't be empty collections of sets. So the minimum that you could have is the filter that contains the whole set X. And then there's the Fréchet filter, or the cofinite filter, that consists of all subsets of X whose complement is finite. If X is finite, this is the improper filter, but it's a proper filter if X is not finite. Now, if you have any sequence in a set X, then you can talk about the eventuality filter of that sequence, and that's just the collection of all sets for which the sequence eventually lies inside those sets. And for any point X in a topological space, there's something called the neighborhood filter for that point, which consists of all sets that contain an open neighborhood of X. Now, filters are a great way to talk about convergence in topological spaces. The main definition is that a filter on a topological space converges to a point little x if that filter refines the neighborhood filter. That's the same thing as saying that the filter contains every open neighborhood of the point. So notice that the eventuality filter associated to a sequence converges to a point if and only if the sequence converges to that point. And so filter convergence generalizes sequence convergence. Now, you can push filters forward through functions. So if you have a function f from a set x to a set y, then you can push forward any filter on x to a filter on y. And I think the easiest way to explain that is to use, to pull subsets of y back to subsets of x through the function. That gives you a map from the power set of y to the power set of x. You view a filter on x as a map from the power set of x to 0, 1. And when you compose, you get a map from the power set of y to the power set of 0, 1. If you break this down, it means that a subset B of y is in the push forward filter if and only if its preimage is in the filter. And this, you can use filters then to give a really nice characterization of continuous functions. So a map between topological spaces x and y is continuous if and only if the push forward filter converges to f of x whenever the original filter converges to x. Okay, let's prove this. So start with a continuous function and a filter script f that converges to little x in the domain. We want to show that the push forward filter converges to f of x. So we take an arbitrary open set around f of x. Because the function's continuous, when we pull that back, it's an open set around x. But because it's an open set around x, it's in the filter script f. By definition of the push-forward filter, since f inverse of u is in script f, u is in the push-forward filter. To prove the other direction, you suppose that you have a function with the property that the push-forward of a filter converges to f of x whenever the original filter converges to x. In particular, the neighborhood filter of a point little x converges to little x. So its push-forward converges to f of x. And this means that the function f is continuous. To see that, you take an open set around f of x, which then must be in the push-forward filter because the push-forward filter converges to f of x. For u to be in the push-forward filter means that its pre-image is in the neighborhood filter of x. And then that means that there's an open set, call it V, containing x contained in the pre-image, which is what it means to be continuous. Now let's compare this theorem that says that a function from x to y is continuous if and only if the push-forward converges to f of x whenever the original filter converges to x, with the sequential version, which says that if you have a continuous function from x to y, and the sequence fxn converges to f of x whenever the original sequence xn converges to x. But the sequential version is not true. The converse of the sequential version is not true. So for example, let x be, take the set 0, 1 to the 0, 1 with the product topology, look at the subspace consisting of integrable functions, and consider the function from x to r defined by integrating over the interval. This function is not continuous, but if you have any sequence of functions in the domain fn that converge to f, their integrals converge. This is a consequence of, for example, Lebesgue's dominated convergence theorem. So this is a function so that it takes convergent sequences to convergent sequences, but it's not continuous. Now let's define an ultrafilter. I think the best way to define an ultrafilter is as a function from the power set of x to 0, 1 that not only respects intersection and the unit for intersection, that's a filter, but it also respects union and the unit for union. If you break down what this means for the collection of subsets of x, it means that it's a filter, it's a proper filter, and satisfies the property that for any set A, either A is in the filter or its complement is in the filter, and not both, or it wouldn't be proper. So how do you see that the function respecting unions gives you this bulleted property? Well, you just say 1 equals f of x, you know that. This whole set x equals A union A complement, which respecting unions means that that equals f of A plus f of A complement. So either A or A complement, f of A or f of A complement has to be 1. Now there are two other equivalent formulations of ultrafilters. The first is that ultrafilters are just maximal filters. And the second characterization is that ultrafilters are just prime filters, meaning that if they contain the union of A and B, it has to contain either A or B. Now, let me pause for just a moment to make an important comment, which is that you can talk about filters and ultrafilters, maximal filters, and prime filters in arbitrary partially ordered sets. And there, the concept of being a maximal filter and a prime filter are different. But for us, we're talking about filters and ultrafilters in the particular partially ordered set that is power set of a given set X. And in that situation, prime filters, maximal filters, and ultrafilters are all the same. And let's prove it. So first, to show that maximal implies ultra, suppose I have a filter that's not an ultra filter. Suppose it's a filter and there's some set A and neither A nor A complement is in the filter. Well, then you can just throw A or A complement into the filter and see that that is properly contained in a proper filter. And so the original filter I had wasn't maximal. In order to prove that ultra implies prime, suppose you have an ultra filter and take a set A union B in the filter, and suppose that A is not in the filter. I want to show that B is in the filter because that would prove that the filter is prime. So since A is not in the filter and it's an ultra filter, the complement of A is in the filter. But once you know that the union is in the filter and the complement of A is in the filter, the intersection, which is a subset of B, is in the filter, and therefore B is in the filter. And now to finish proving the equivalence, I want to prove that prime implies maximal. Let's start by assuming we have a filter F that's not maximal. So it's properly contained in a proper filter G. So there's some set A that's in G, the filter G, but not in the filter F. Now notice if A is in G, the complement of A cannot be in G because then the intersection, which is empty, would be in G, and G would contain everything and it wouldn't be proper. So the complement of A is not in F either because everything in F is in G. So we have A not in F and the complement of A not in F. But the union is in F because the union is just X and X itself is in every filter. This proves that the filter F is not prime. Now, as I said, filters of sets are special because ultra filters, maximal filters, and prime filters are all the same. And what's nice is that for certain purposes, maximal filters are really great. And for other purposes, prime filters are really great. So let me state the ultra filter lemma, which says that every proper filter is contained in an ultra filter. And there's a straightforward proof of this fact using Zorn's lemma if you use the characterization of ultrafilters as maximal filters. And one way in which the ultrafilter lemma is commonly used is if you have a collection of sets with the property that no finite intersection from that collection is empty, then you can take all the finite intersections, and that's downward directed. Then you can upward close it by containment, and that will give you a proper filter that by the ultrafilter lemma is contained in an ultrafilter. Now, principal filters on infinite sets are always ultrafilters, but a corollary of the ultrafilter lemma is that every infinite set has a non-principal ultrafilter. And you can prove that by taking the Fréchet filter on an infinite set. And then that, by the ultrafilter lemma, will be contained in an ultrafilter. And the resulting ultrafilter cannot be principal. In fact, it can't contain singletons or any finite sets because it contains the complements of all the finite sets. The converse is true too. It's good to know that any ultrafilter containing a finite set is principal. My notes here say any filter containing a finite set is principal, but it should say any ultrafilter containing a finite set is principal. Now, for another theorem, we have that the push forward of ultrafilters are ultrafilters. Now, the best way to see this is to use the characterization of ultrafilters as prime filters. And to see that prime is respected by push forwards, just remember that the push forward of a filter is really the composition of the filter with a function that respects unions. Now, another really great theorem that you can prove about ultrafilters that relies on the characterization of ultrafilters as prime is that a topological space X is compact if and only if every ultrafilter on X converges to at least one point. And the way you do this is you assume that you have a prime filter that does not converge to any point. Then you can find an open cover of your space that has no finite subcover. And you see for each point, there's an open set around that point that is not in the filter. then this collection, if it had a finite subcover, the union of that finite subcover is all of X. That is in the filter, and by primality, at least one of these open sets would have to be in the filter. And in the other direction, if you have a space that's not compact, then it has an open cover that has no finite subcover. You can make an ultrafilter out of that by taking the complements of all the sets in the open cover. That collection of sets has the property that no finite intersection is empty, and so so there's an ultrafilter that contains it, and then that ultrafilter can't converge to any point because each of those points is in one of the open sets in the open cover, but that open set can't be in the filter because its complement is. And this characterization of compact spaces as those spaces in which ultrafilters always have limits is a really great characterization because it gives you access to really elegant proofs of theorems that otherwise would have more difficult proofs. So for example, Tikhonov's theorem, which says that the product of arbitrarily many compact spaces is compact, and then prove that any ultrafilter in the product has a limit. And you do this by looking at the push forward of that ultrafilter to an ultrafilter in each component. And those, because those components are compact, those ultrafilters have limits. And then you can find a candidate limit for the ultrafilter in the product space. It's just the point in the product whose components are the limits of the push forward ultrafilters. And if you want to see that this ultrafilter converges to this point X in the product topology, what you can do is you can take one of these sub-basic open sets in the product topology that look like the product of the whole space is X alpha, except in one component, it has a little open set around X beta. Call it U beta around X beta. But because U beta is an open set around X beta and the push forward limit converges to X beta, that open set is in the push forward filter, which means exactly that its pre-image is in the original filter, but its pre-image is that open set around X in the product topology. Now, another really great theorem you can prove is that a space X is Hausdorff if and only if every ultrafilter on that space has at most one limit. And you can prove this by supposing you have a Hausdorff space and an ultrafilter. If you take two different points, X and X prime, the ultrafilter can't converge to both because there are these disjoint open sets that separate the 2 points. And the ultrafilter can't have both of them in it because it would then have the intersection in it, which is empty. That's not possible if the ultrafilter is proper. And on the other hand, if X is not Hausdorff, there exist 2 points, X and X prime, so that the intersections between every open set around X and every open set around X prime will be non-empty. Well, since those intersections are non-empty, that collection of intersections sits inside of an ultrafilter, and that ultrafilter will converge to both X and X prime. Now, I think it's nice to put these two theorems together and look at them at the same time. A space X is Hausdorff if and only if every ultrafilter has at most one limit. And a space X is compact if and only if every ultrafilter converges to at least one point. And so you see that there's this tension between being Hausdorff and compact, and spaces that are both compact and Hausdorff have a nice balance. In particular, they're characterized by the property that every ultrafilter on them converges to one and only one point. And this concludes this video on filters and ultrafilters in topology. Thanks for your attention.